Okay, this is a nightmare of keeping track of all my numbers and signs. So I want to use determinants. For me, this is a lot clearer. You can do whichever you like. Two methods of solving a determinant, but I want to write my determinant R cross F in this format. I, J, and K in the top row, the unit vector really in the top row. The position vector goes in the second row, Rx, Ry, and Rz. The force vector, the components of it, go in the third row, the bottom row, Fx, Fy, and Fz. Okay, remembering back from math, the way I evaluate a 3x3 determinant is I multiply the first component of the top row times, which I've circled in red, I, times this little 2x2 determinant below it that I've put little red lines to determine, to show. You multiply I times the determinant, the 2x2 that's not directly under it. The components are not directly under it. So for I don't want to consider Rx and Fx. I want to consider Ry and Rz and Fy and Fz. So I've kind of written it out over here more clearly. I times this little 2x2 grid, and then that's plus I minus J times not the column right below it, but the two columns not below it. So I've put this Rx and Rz over here, plus K, left my plus sign out there, but it's plus K. It's plus I minus J plus K. Plus I minus J plus K. K times the little green determinant, 2x2, Rx and Ry and Fx and Fy. Okay, so remembering that I'm going to evaluate, I kind of skip down here to the blue, I evaluate a 2x2 determinant with Ry kind of across the diagonals. Ry diagonally times Fz plus, that's plus Ry times Fz, minus Rz times Fy. So I've written it out here. Ry times Fz, positive, minus Rz times Fy. These are just scalar numbers. I'm just multiplying them together and adding or subtracting them up. We'll see an example down here, a 2x2, and then a 2-dimensional, and then we'll do a 3-dimensional later. The other way, method 2 of evaluating a determinant, is to start off with same thing, IJK, unit on the top, position in the middle, force on the bottom row, and then I repeat the first two columns of this determinant. So I just take this I column, IRX, Fx column, and put it there, the J, Ry, Fy, and put it there, and then I evaluate it diagonally down, I times Ry times Fz, minus, I have to go over here to get my minus, J minus I column, minus I times Fy times Rz. And I repeat that for the J and the K, and I rearrange, gather my terms together. I'm going to come up with the same expression, Ry times Fz minus Rz times Fy, the whole thing times I, and so forth. Repeat that whole process of evaluating the determinant. I end up with this thing here, which is a scalar minus a scalar times I, scalar minus a scalar times J, or minus a scalar plus a scalar times minus a scalar times K. It's exactly the same thing as I got up here, the other way of multiplying everything out. I ended up preferring, I like this method. Just do these little 2x2 determinants and multiplying them by I, J, and K. I plus minus J plus K. Do it however you want to. Finally, we get to an example. We'll start off with a simple two-dimensional cross product example where I've got a y-x coordinate system. I'm given force F at 260 newtons at point A, applied at point A, which is the coordinates of 6 and 6. further I have to give you some sort of direction with this magnitude, because a vector is a magnitude with a direction. I want to find the moment about the origin O and the shortest perpendicular distance to that vector F from point O. Okay, so I want to express F in Cartesians, the vector F. The components Fx is negative, because it's going to the left, 12/13. I've given this direction slope 12/13. Negative 12/13 times 260 is negative 240 newtons. Fy is similarly 5/13. Opposite over hypotenuse. Negative 5/13 times 260 is negative 100 newtons. Negative x because it's to the left, negative y because it's down. Then I write my position vector from O to A, so that becomes the nomenclature is RA over O. That's just really these coordinates, 6i and 6j. And now I'm ready to write my determinant, which looks like this: ijk, unit vector, position vector 6, 6, and 0, force vector negative 240, negative 100, 0 on the bottom. The i's go to 0 because I have 6 times 0 minus negative 100 times 0. The j's go to 0 because I have 6 times 0, 0 times negative 240. So the only thing that gives me a value is k. K is just this little 6, negative 240, negative 100, 2 by 2 determinant. I evaluate that as 6 times negative 100 minus 6 times negative 240. Those are just scalars. I'm just multiplying them together. I get negative 600 plus 1440, and that's equal to 840 Newton meters in the k direction. The positive sign means using the right hand rule, it's coming out of the board at me, so my fingers curl in the direction of positive moment, and that is counterclockwise. Now I want to figure the shortest perpendicular distance, and it didn't draw it really very well. If I was to continue this line on out, I want to find kind of, it looks like that is DO, the shortest perpendicular distance. If I extend it on out there, if my drawing is close to scale, and it kind of is, it's going to look like that. And I just take the scalar magnitude of the moment divided by the scalar value of the force. 840 over 260 is equal to 3.23 meters. And you can see that's kind of about right if that's 6 and 6. Okay, I also want to take my scalar method and check my number here. Remember there, I just multiply numbers together and keep track of the direction of the moment. If I'm using Fy, which is 100 from up here, times its x distance of 6, and I look at that and I say that's going clockwise moment, so I make that little arrow below it. And then this, the Fx, which is 240, is causing counterclockwise moment. Its moment arm or distance Ry is 6, so it's negative 240 because it's the opposite direction of what I started off with, which is clockwise, so it's counterclockwise. Make that little arrow. Do the math. 100, that's 600. Same numbers up here as I got 600 and 1440. And so it's negative 1840. The negative means it's the opposite of what I assumed is positive up here. So positive for the here was clockwise, so this negative means it's counterclockwise, so that checks out with my determinant method of solving the cross product. Finally, let's find the moment about point B down here. It's 3 and negative 2, and my force is still the same. I do a position vector R A over B. The tip is A, tail is B. Coordinates of A minus B, 6 minus 3, 6 minus negative 2 gives me a position vector of 3i plus 8j. Here's my determinant, ijk, 3, 8, and 0 for my position vector in the middle row. Negative 240, negative 100, and 0 for my force vector on the bottom. Evaluate it similarly to this. Similarly, k times this little 2 by 2 determinant. 3 times negative 100 is negative 300, minus negative 240 times 8 is negative 1920. I've skipped one little step here that I did up there. Do the math. This works out to be positive 1620 k direction Newton meters. Positive means put my hand on there, my thumb points in the positive direction, so the curl is counterclockwise. That's the direction of that moment, which is not surprising, same direction as the moment it creates about point O. I'd have to have a point somewhere up here to get a negative moment or a clockwise moment, which you can kind of see. If I had a point up here, it would be creating clockwise moment, and I would get a negative number. Lastly, the shortest perpendicular distance between the force vector and point B is kind of, waited till now to kind of draw this. It might look like something like that, where that's perpendicular. That would be dB, and that's equal to the moment divided by the force. 1620 divided by 260 is 6.23 meters.